This video I will show how to read and understand a few chemical engineering problems and then convert those chemical engineering problems into linear programming problem, or we can call it as how to convert a chemical engineering problem into recipe for LPP. Yeah. So this is my own terminology which I use for convenience. So recipe for LPP. So you need this recipe in order to implement some of the algorithms that we already learned. Yes, for example, corner point method, isocost method, or even simplex algorithm. So we need some recipes in it, to solve those. That looks like a linear programming problem. To convert a chemical engineering problem into LPP, first you have to understand the chemical engineering problem itself, isn't it? Yeah? So let's do that one by one. So you have to spend some time in trying to read the question and then understand the question, make sense out of some of the, the conditions that we set in this type of problem, and then you have to convert them into set of linear equations, which is typically your cost function, and then into some of the linear inequalities which correspond to some of the constraints associated with the problem. So let's read the first one. So what we have here, a cooling tower in a chemical plant requires at least 3 meter cubes per minute of water supplied by two parallel pumps, pump A and pump B. So which means there is some water demand, which is equal to 3 meter cube per minute. So let me write here. So there is some water demand, 3 meter cube per minute. So you have to achieve this using two pumps. They're operating in parallel. So they are pump A and pump B. And pump A delivers approximately x meter cube per minute. So pump A delivers x meter cube per minute, and then pump B delivers roughly y meters cube per minute. So these guys will become the decision variables. And then due to hydraulic constraints in the shared discharge header, so there are some hydraulic constraints due to the shared discharge header, the pump outputs must satisfy some conditions. So here this is something that already looks like a linear inequality. So there is some constraint. That's why you have some linear inequality symbol here. So what do I mean by that? So the hydraulic constraint. So what this exactly means? So in many chemical engineering plants, the pump, even if you have two pumps, in this case A and B, and they are operating in parallel, and they are pumping something at some known flow rate, say for x meter cube per minute and b y meter cube per minute. So they often share. So they often share the same pipe outlet. So imagine there is a pipeline, and the exit from both the pumps goes to the same outlet pipe. So this is something called as a discharge header. This is something called as discharge header. So that's the meaning of this. And then so both pump A and pump B are trying to push the water into the same pipe, which is here. Their flow can affect each other, and then what we have here, this the piping system cannot take any combination of flows. So instead it have some hydraulic limit. So that's the meaning of this one. So since we have the same discharge header, there is some constraint for the with respect to the hydraulic limits. Both pump A and pump B so cannot operate at full capacity. So at the same time, and that's because we are sharing the exit pipe. Sometimes we call it as a discharge header. So which means this pipe cannot handle that hydraulic load, and that's why we have some constraints. X minus 2y is less than or equal to 2. And there is a second constraint. So what is the second constraint? Okay, let's go into the something related to the cost. So the electricity cost to operate pump A is $3 per meter cube per minute. So if you're going to deliver like 1 meter cube per minute, then you have to spend something at around $3. And then to operate the pump B, in order to maintain a flow rate of 1 meter cube per minute, you have to spend roughly $5. Okay, so you have something related, some information which is more than enough to write something called as the cost function. So if you define Z is the profit or sometimes we call this as a cost function. So this is something we can write like 3 times the x is nothing but how much we deliver using pump A per meter, how many meter cubes of water we deliver using pump A per minute. 3x plus, so we spend $3 in order to deliver 1 meter cube per minute, and then we spend $5 in order to deliver 1 meter cube per minute using pump B, and we spend $3 in order to deliver 1 meter cube per minute using pump A. So that becomes your cost function, where x and y are called as the decision variables. In LPP language, z is sometimes also called as objective function. And there is another constraint to this problem. So to prevent the pressure fluctuations in the pipeline, the pump must satisfy, what is that? The pump must also satisfy minus 2x plus y less than or equal to 4. We have to maintain some flow balance so that the discharge header, which is this pipe, this is the common pipe, no, where the exit from A and B meet. So where there is no hydraulic restrictions, when the two pumps are operated, when we are operating two pumps together. So that's the approximate meaning of that. So in order to avoid some pressure instability in the pipe, you say that so if you cannot pump something using pump A and pump B at any flow rate, so that could create some unnecessary pressure or maybe some vibrations in the pipeline. So this is something that you should avoid, and we set some constraints for that. So that's something which is already written in the form of a linear inequation, minus 2x plus y, which is less than or equal to 4. So now we have the LPP recipe. So let's write all the linear equation, which is your cost function, which is something already written here, and then you have one linear inequality with respect to the hydraulic constraint, and then you have one more linear inequality with respect to pressure, the target to prevent pressure fluctuations in the pipeline. So let's write that x minus 2y less than or equal to 2, and another one is minus 2x plus y less than or equal to 4. And then if you go to the very first line, so the chemical plant requires at least 3 meter cubes per minute of water supplied by two parallel pumps. So there is pump A and pump B, so which means there is one more constraint. So you have to meet at least 3 meter cubes per minute. This is something we can call it as the water demand. So x plus y. So both pumps should pump something so that the total should be equal, at least equal, should be less than or equal to 3 meter cubes per minute. So that's the LPP recipe that we created from this chemical engineering problem. And let's create, let's do the procedure for the example 2. So this is something related to formulation. So let's read the problem. Sorry, a chemical plant produces a high-value specialty chemical using two different formulations, formulation A and formulation B. So each formulation requires different outcomes of labor, equipment time, reactor time, and utilities. I think this will become the some constraints with respect to formulation A and formulation B. So let's say x1 is the number of batches of formulation A produced per day. Formulation is something like you take some pure chemical and then you convert them into a finished product. Yeah. For example, paracetamol, typically we get it in a powder form, and then we have to convert them into tablet. Yeah. So tablet is something we can call it as a finished product. So let's say we can make a normal tablet, another one say something like a capsule. So these are two different formulations, A and B. Yeah? So that's the meaning of formulation. Let's say X refers to the number of batches of formulation A produced per day, and then X2 refers to the number of batches of formulation B produced per day. So X1 and X2, and then there is some information about the revenue that we generate. So formulation A generates a revenue of $15 per batch, and formulation B generates a revenue of $10 per batch. Yeah. And then the plant faces the following operational constraints. So let's write the cost function first of all. So the revenue that we generate from formulation A is 15 and per batch, and then we generate roughly $10 per batch using formulation B. So we can write the cost function something like z is equal to 15 times x1 plus 10 times x2. So as for every batch you get $15 through formulation A, and then for every batch you get $10 via formulation B. So that's the meaning of that. So we already completed or managed to write the so-called cost function, and now let's write the linear inequalities, yeah, in order to convert this entire problem into one LPP. So the total operator and equipment time constant. Formulation A requires 4 minutes of operator plus equipment time per batch, and formulation B requires 6 minutes per batch. So with respect to operational constraint, so what we have here, so 4 times the x1 plus 6 times the x2. This is something which is given here, and the plant can supply a maximum of 360 minutes per day of operator and equipment time. So which means there is some restrictions here. So formulation A requires only 4 minutes of operator plus equipment time per batch, and formulation B requires 6 minutes per batch. Yeah? So this is something related to the time, and the plant can supply only a maximum of 360 minutes per day. So which means 4x1 plus 6x2 should be less than or equal to 360. So this is one linear inequality, and there is some other constraint related to reactor availability. So this is only for the formulation A alone. Yeah? So formulation A requires 3 minutes of reactor operations per batch. Yeah? So what does that mean? So it requires at least 3 minutes of reactor operation, reactor time per batch, and then the reactor is available a maximum of 180 minutes per day. So in a day you can use only 180 minutes. Yeah? So maybe we will use the reactor for other purposes. So what does this mean? So how do you write this into an LPP constraint? So formulation requires 3 minutes of reactor time, so which means 3 times x1, and this is less than or equal to 180 minutes per day. Okay, and then there is some restrictions for the utilities. So to convert something into some finished product via formulation B, something we can call it as, say for example, capsule. So this may require 5 units of utilities. The utilities can be anything. I just listed some of the common utilities. So we need roughly 5 units of utilities per batch, and plant B has an upper limit of 200 utility units per day. Yeah? So which means 5 times the x2. So you need at least 5 units of utilities for formulation B, isn't it? Yeah? And we have an upper limit for that. So this should be less than or equal to 200. And then we also have the common non-negativity constraints, x1 greater than or equal to 0 or x2 greater than or equal to 0. So there is something we produce either via formulation A or formulation B. So this is something I forgot to mention. Even in the previous problem, example 1, you have to include the non-negativity constraints. Yeah? So in this case, x should be greater than or equal to 0, and y should be greater than or equal to 0. What does it mean? Which means we have to pump at least something using pump A and pump B. So that's the meaning of that. Okay, so now we have for example 2, we have a cost function, we have constraint 1, we have constraint 2, and then we have constraint 3, and then the usual non-negativity constraint which is placed here. Yeah? So 1, 2, 3, 4, and 5. So all of them make the LPP recipe, which we can solve using any of the algorithms that we learned. You can use the corner point method, isoprofit method, or the simplex algorithm. Maybe we will see a few more algorithms. Yeah? There are many useful algorithms that we can learn to solve a LPP, which is a linear programming problem. So 3x1 less than or equal to 190. This is something you can write something like x1 less than or equal to 180 by 3, which means less than or equal to 60. So similarly, you can also write this one, x2 less than or equal to 20 200 by 5, so that makes it less than or equal to 40. So x2 less than or equal to 40. We can solve one more problem, something related to solvent mixture preparation for a crystallization process. So crystallization is something that we use to manufacture most of the pharmaceutical compounds, and because most of the pharmaceutical compounds that you buy in the pharmacy, they are generally produced in crystalline format for a good reason. We don't have to go into the details about the crystallization, but the idea of the problem is to know that for such a process you need typically we will use a solvent mixtures, yes, in order to manufacture that crystalline product. So let's say for crystallization you need a solvent mixture made by two solvents, say solvent A and solvent B, and X is something that refers to the volume of solvent A in liters, and Y refers to the volume of solvent B, and we need to mix them to make the solvent mixture. And we have some details. For example, here you have something like a total volume, like a total solvent volume in the crystallization process. It's something given by um, z is equal to x plus y, and our intention is to minimize the solvent requirement in order to manufacture a product using crystallization process. So the cost function is already given, z is equal to x plus y, and let's assume we need to minimize this cost function. So that's our objective function at the moment, and there are some constraints. So solvent B must never exceed the amount of solvent A. So because too much of solvent B would redissolve the crystal. So what do I mean by that? Sometimes if you have more solvent B than solvent A, there is no number specified here. But if you have too much of solvent B than solvent A, then it will dissolve the crystals back. You don't get any product outside. So when you filter, you don't get any solid product. So that means mathematically you can write Y should be less than or equal to X. So which mean so Y cannot exceed X. So the liters of B cannot exceed the liters of A. Sorry, yeah. So that's the meaning of that. So Y should be less than or equal to X. So you can write this in the form of minus X plus Y is less than or equal to 0 or equal to 0. Yeah, less than or equal to 0. So you take the x this side here, so minus x plus y is less than or equal to 0. So that makes one constraint. And another one is there is some safety requirement. Yeah? So the mixture must also contain solvent B, more solvent B than solvent A, at least by 1 liter. Yeah? So which means Y should contain the liters of B. So the liters of B should be greater than or equal to x plus 1 liter. Yeah. So that's the meaning of that. So that means Y should be greater than or equal to x plus 1. So that's the second condition. This is a very weird problem. Yeah? So even if you try to solve it using the graphical method, you will see that there doesn't exist any feasible region. Yeah? So which means this cannot be solved using LPP procedures. Yeah? So or any of the algorithms that we commonly used to solve LPP problems. So y greater than or x, y should be greater than or equal to x plus 1, or if you want you can take the x this side, minus x plus y should be greater than or equal to 1. So this is second constraint. Yeah? And then you can have non-negativity constraints, x greater than or equal to 0 and y greater than or equal to 0. So that's how you convert the chemical engineering problem into LPP problem. So if you want, you can try to solve all the 3 examples that we studied now using any of the algorithms that we learned so far. Yeah? So you can try corner point method, you can even use the graphical method, or maybe you can use a simplex algorithm. Yeah? And then you can, for example, example 3, if you try to solve, you will understand that it will be really impossible to solve this particular problem. Yeah? So that's enough for the moment. Maybe I will create one more video. Maybe we will try to solve a few more example problems, or we will try to convert some more problems that we take from the optimization book written by Himal Blau. For example, we can solve this problem at 7.1, or you can try it yourself. And then we can solve one more problem that looks, for example, 7.3. So this is something we can solve, and another one can be, oh, maybe that should be enough. Yeah. So maybe I will upload one more video where I will show how to convert this chemical engineering problem, something related to a petroleum refinery, into an LPP problem, and then we can solve one more problem, something related to some reaction happening in a reactor. Yeah. So this is something we can see in a separate video. Thanks for listening.